All right, what's up, guys? I'm going to just like do a very short video on this extra credit assignment. Um, I don't think that it looks too bad, and you can always email me or reach out if you have this, but I I'm not even gonna look at the actual assignment itself because what I don't want to do, right? I want to let you fight with it out, but like I think watching this is gonna help. So without too much, so um, first thing I'm gonna do is I'm just gonna simulate the circuit, right? And part of me not doing it like for you because this is something I'm bad at, right? Like I always or you they just end up doing the problem when they come. Trying to be better about that. So we're starting today. But we're gonna simulate it, right? And part of me not going through leaving you with nothing to do is going to be me just using random values for like the resistances and stuff and the battery. So what I'm gonna do is I'm just gonna circuit. So I think it looks something like this. Let's connect that, and then we have another one. Okay, and then let's circuit out with some wires. This and that. Let me zoom in. Seems kind of small. Um, so let's just do this. Let's edit the battery. I don't know. Make it 10 minutes. And then what we're gonna do is we're just gonna go through and we're gonna make these. So I'm gonna make this one 2K. This one 3. And we'll just keep going 4, and then the last. So there you have it. Right, and now we kind of have an idea of what's happening here. You notice that in the simulator, right, the little yellow dots flowing is kind of like it's well, it is current, right? That's what it represents. I almost said that it's the electron flow, but it's not, right? Because because Ben Franklin, but it's fine, right? But the reason that we can see that it's not, is these if these were electrons from high potential to low potential, right? It would be, but also protons. So that's the anyway. That's a different story. It, um, Okay, so this is what we have. We kind of have an idea of what's going on. Some current sort of comes out of the battery, comes around here. It splits somehow here, right, at this node. Um, and then this would be a rather simple circuit to analyze if you didn't have this resistor going horizontally across. Right? This is kind of what's messing everything up, right? And we see that there is current flowing there, so this sort of suggests that generally current will flow there, and we can't just kind of ignore. And then there's current, coming from this node through the 4K ohm resistor, and then going on 5K ohm, right? So, I mean, what we're gonna do is we're just going to uh, apply Kirchhoff's loop rule, right? And it's not. I don't think it's too terribly difficult. Um, but you want to be very careful when you equation. Um, so let's look at what that involves. Give me a second. What I'm gonna do, I think, is take this circuit. Wow, that's right, but fine. Um, so I'm just gonna take a picture of this and put it into Paint and then sort of sketch what the currents. So here we have it. Let's glory. And I'm just gonna go through and I'm gonna say something like, well, we have I1 that is flowing like this. And then we'll call this I2 here that's flowing through the 1K resistor. Call this I3 it's flowing through the 2K resistor. Then I don't remember which way this is going. I think it was going to the right, though it doesn't matter, right? Because you can always see when you guess incorrectly uh, after you go through and you solve for the numerical values, right? Because we find that, say, the current negative, then we know that we correctly. So it doesn't really matter, right? So I'm just going to do this. I'm going to say I4 goes this way, right? And then let's see, call this I5 down here, 4K resistor. Call this I6. And then of course we have I1 now again back out because so what we end up seeing here is we're going to come up with a variety of equations, right, involving the current, because I think we all know that in this situation, let's say the change in voltage across, let's say, the nth resistor is going to be, and I'm going to put a negative sign in, right? It's negative IN RN, right? Because we're always, or how do I say this? Because our current is always going in the direction of our loop, right? And I didn't specify this, but our loop is going to go like this, right? Our loop is going to go clockwise around the circuit. Okay, so we just have to come up with the equations here that are reflected by what we've written. Okay, so what that looks like, right? And I don't know that I'll go through and do all of them. Is something like I1. Well, here, right at this black dot, this node, we see that it splits into I2, right? That I1 is uh, I2, I3, like so, right? Now, if we focus on this one here, we have that I2 breaks off into I4 and I5, right? So that's 4 plus I5. And then if we look at I4 and I3, right, we see that they combine here. So we can write that I6, I3 plus I4. I'm feeling kind of lazy, so I'm not writing. Hopefully, I don't think it's too bad. It's just a little while to make it legible. Um, then the last thing again, right, is that I1 equals I5 plus I6. Okay. So we have all these unknowns, right? The currents at this point are all unknown. And we will have enough equations, right, to solve for every one of them. Let me just make sure all the equations. I1 is I2. That looks I2 equals I4 plus I5, sure. I3 plus I6, and then I1. Yeah, I don't think there are any other equations we can come up with here that are going, right? This should be an exhaustive list. The last equation, of course, is going. Actually, we could do. How many loops could we? We could do one that goes left, right, and avoids this middle resistance. One that goes right, avoids this middle resistance, and then one that maybe goes through and uses the middle resistance. Okay. Um, So we'll write some of those out too, I guess. Okay, so let's just write those out, and then I'll probably leave it at that. Actually, go through and do math because this is just a lot of algebra and mathematics, very easily. So one of our loops is going to be if we go clockwise around, right? Um, we're going to have uh, an increase in voltage of the battery, right? Whatever it was, from the low plate to the high potential plate. And we're going to say minus, right, um, I2, and I will call this, I'll call it R2, right? I'll just make the numbers of the resistance correspond to the numbers of the, and that's kind of going to go nicely with what I wrote up, right? So R2 is this I2 going. Then we'll have minus I5 R5 equals 0, right? Because after we pass through this resistor here, R5, there is no element uh, through which the current passes to make the drop again, right? And that's why, like when we're writing out our loop rule equations, we're actually not going to see I1 appear in them because I1 itself does not go through any resistor, right? Or through a battery or anything, even though it wouldn't really be a battery. But let's do the other loop then. This is going to be EMF of the battery minus I3 R3 minus I6 R6. This is 0, right? And then we could do one more. We could go up by the EMF of the battery, and now we're going to go through this middle resistor. So we're going to write, it doesn't matter which way we go, but let's say we go into this node here. We go down through R2, then we go through R4, and then we go through R6, right? So this is going to look like um, EMF minus I2 R2 minus I4 R4 minus I6 R6. So this is our list of equations basically that we're going to need to work with to figure out what these numerical values are. Okay. Um, and while I'm not looking at the document right now, I do remember him saying something about like the equations being redundant, or there's something he put in there, right? Uh, I don't really know what he's getting at with that, but the point is that this is definitely solvable, right? You just need to make sure that when you're trying to make, say, Mathematica do it, that you give it the same number of equations, the same number of unique equations as unknowns, right? Because if you don't, it's going to get mad, and we don't like it when our computer overlords get mad at us, right? It's not a good time. So there's that, right? There's actually going through and solving this, and you can see kind of maybe that um, how do I say this? Here's my gut feeling, right? And I'm gonna let you struggle with it a little bit. But my gut feeling is that these two equations that I wrote for I1 um are the sort of extraneous ones in a sense because again I1 doesn't appear in any of these loop rule equations, right? So you might just focus on the equations for I2 and I6, which I'm drawing a dashed box around. So, right, and we just need to make sure that we have as many equations as unknowns. And we have uh and it's weird because we kind of have I1 as an unknown, right? But it's not really unknown in principle, uh, because we know that either I2 plus I3 or I5 plus I6, right? So I think that with these two equations, right, that's two equations, these three here, that makes five. We can solve for I2, I3, I4, I5, I6, and then getting I1 is a simple matter because it's equal to either I2 plus I3 or I5 plus I6. And I mean, I should be careful with my language here because it's equal to both of the sums that I just mentioned, right? Uh, it must be because the current has to be served, right? Um, so that's, I mean, that's pretty much it here, right? You have to go through and you have to, like maybe build the circuit in your little, lab kit. Write some words about why you're doing what you're doing, stuff like that. But this is pretty much it. The last thing I want to show you though is that on the simulator, I suggest that you uh use this not to, you know, just get the answer right because you won't get credit that way anyway. We're going to want to see your work. But you can use it to confirm that what you're doing is correct, right? So, and what I mean by that is I can put like ammeters in the circuit here. Just careful. So I can take, for instance, this 5 kilo ohm resistor, and I can make in series with it an ammeter, and that's going to be, I think, under inputs and sources. No, sorry, outputs and labels. Definitely not inputs and sources. Outputs and labels. I can draw this in, right? And now it's showing me what the current is through that. And you could do this for every resistor and just use this to confirm that your work is correct, right? Now, maybe just one last thing to say about solving equations in Mathematica is, again, that you need the same number of unknowns as equations. And they have to be unique equations. You can't just, write one equation and have like another equation where everything is just the negative of the first equation, because that's not unique. But like the way that you do this in Mathematica, everybody should know this by now, but just in case you don't, is you just type solve, right? Square brackets. And you have to make two pairs of curly braces. So inside this pair of curly braces, your equations go. So I might write like x plus 2y plus 3z equals a or something like that, right? And then I do a comma for the other equation. So if you use Mathematica to solve this, you're going to have, I think, 5 equations in here. So then I should write like something like plus 4u minus 6w or something like that, right? So that I have 5 unknowns there. And then you're going to keep going, right? You're going to write the rest of the equations. That's what I'm symbolizing with the 3 dots. You have to remember to use a double equal sign, right? When you're trying to make Mathematica solve a system of equations. And then over here, we would have like x, y, z, and w. And then, you just shift enter and I mean, I could just try this right now, right, with only one equation there and 5 things to solve for. And here you go. This is what it's saying, right? It's saying, look, idiot, we don't have enough information to solve for, 5 separate variables, right? And that's what the little error message is saying. Another thing to note really quickly too is that if you try to use I, like just a capital I, Mathematica is going to interpret this as the imaginary unit, right? So Mathematica takes capital I to be square root of -1. And as far as I'm aware, you can't change this, right? And just to prove this to you, if I put I squared in, it gives me gives me back -1. So if you want to use eyes uh, in your work in Mathematica, what you can do is you can do escape and then shift, hold down shift I, and then just use the iota, right? Because this looks almost exactly the same as a capital I. But now this Mathematica won't take this to mean the square root of -1. So like for instance, if I just tell it, hey, tell me what iota squared is, it just gives me iota squared back, right? It doesn't give me negative. And I think that should be everything you need to do uh, to sort of figure out how to get through this lab. And if you have any questions, as I said, feel free to reach out. Hope everybody has a good spring break. I know you were all very worried about me, but I think I'm finally starting to feel better here. It's been a rough couple days, but yeah, um, I will see you next week then.